Hi, my name is Celi Johnson, and I will be presenting on the findings of an experiment conducted on a Reicha tube. We studied the properties of a Reicha tube to understand the relationship between heat release energy and acoustic sound. This relationship is known as thermoacoustics and an important relationship in physics. A Reicha tube involves heating a wire mesh in a metal pipe, as pictured on the bottom right. It functions due to the chimney effect, or the convection of hot air oscillating. Pressure changes due to heating, and the natural oscillation of imperfect heating, such as the combustion of propane in this experiment, create a self-amplifying sound wave that quickly becomes very loud. The experiment was conducted using the Reicha tube schematic shown. A translatable propane burner, noted by the arrow, was placed a quarter way up the length of the tube, denoted as 0 inches relative. 3 acoustic pressure transducers were placed at this location, 18 inches above and 18 inches below, as shown by the stars. These transducers collected data and were connected to an oscilloscope. In addition, a photomultiplier tube was connected, and using the photoelectric effect, also supplied data. The photograph is of the actual Reicha tube setup depicted in the previous schematic, active in the experiment and burning propane. The measurements of locations are presented in the table, and the Reicha tube total length is presented as it is essential for calculating its resonance frequency. This video demonstrates the experiment in progress. The flame profile and a loud acoustic ringing can be heard with the burner at the 0-inch location in the closed valve. The flame turbulence and pulsations were observed using human senses. Pulsations were observed to stop when the tube stopped emitting a ringing noise. The frequency, amplitude, and phase angle measured by the photomultiplier tube, as well as 3 transducers, were calculated using measurements taken from experiments. Data was measured with the burner at 0 inches with the valve closed, at 0 inches with the valve open, at 2 inches with the valve closed, and was slowly raised until it ceased pulsating at 6 inches. Then the burner was brought back down until it resumed pulsating, which it did not do until it reached -6 inches. The tube was pulsating and the flame was turbulent at 0 inches and 2 inches with the valve closed, but made no audible noise with the valve open or at 6 inches. In the amplitude calculation equation, the SPL stands for sound pressure level of an acoustic field. PRMS is the root mean squared fluctuation of the pressure field, and PRMS threshold is a standardized value of the threshold of human hearing. In the case of this experiment, we used the PSI constant value of this threshold of 2.9 times 10 to the -9th. The pressure was found using the average sensitivity value of 96.8 millivolts per pound per square inch. The speed of sound was required to calculate the resonance frequency of the Reicha tube, and depends on both the substance being traveled through and the temperature of the medium. In our case, air. Knowing the speed of sound, we can use the Reicha tube's length, given as 6 feet, to calculate its resonance frequency of about 94 Hz. Using the first equation from the previous slide, voltage values from the transducers can be conveniently converted to first pressure values, then decibel values. The relative phase of the transducers with respect to the middle one, where the burner was, as well as the photomultiplier tube, are also presented. The amplitudes from the previous slide are once again shown, but the peak frequency recorded by each transducer at each location is also shown. Noticeably, the frequency value is low when the valve is open and there is no noise, at 6 inches, and is very close to the calculated resonance frequency of 94 Hz when an audible noise is heard. Can a 415 to 450 nanometer filter be used? It depends on the intermediate steps of the reaction occurring in combustion. Interference filter that detects within the 415 to 450 nanometer range detects methane or CH products, which may not be a reliable byproduct of propane, so it may not be the best idea in this experiment. And how would we design a tunable Reicha tube? Adjustable length. It's the easiest way. The frequency depends on the speed of sound and its length, thus it's a lot more practical to adjust its length rather than trying to change the pressure or temperature to make a change in the speed of sound. It's also less predictable. The behavior of the Reicha tube aligned mostly with theoretical expectations, with small random errors due to imperfect conditions like turbulence, etc. Practically, the relationship between heat and sound is extremely helpful in the field of thermoacoustics. A A Riga tube is a rather simple thermoacoustic system, but others such as heat engines or combustors are better understood with the basic knowledge of thermoacoustics. Furthermore, knowing the instabilities and negative side effects such as loud sound that arise in these systems are essential in creating safe engines in other systems. Pictures from the presentation were taken from a variety of sources. And thank you for your time and attention.